Hi, welcome back to the channel. Today I'm here with another video which is related to bolted joints, a very important topic both in academia as well as in industry. In industry, you see bolted joints very often. So here I have some pictures of the bolted joints. And in this video, what I will be addressing is how the loads will get transferred to the bolts, or how the load distribution in the bolts will look like when the bolted joint is subjected to a bending moment as shown over here. The direction of the bending moment is too important because the distribution is a very strong function of the way in which this bending moment is applied. So when you have a bending moment acting this way, it tries to open up the flanges. So you essentially need your bolts to make sure that there is no leak and to make sure that the joints are held in place. One strategy that has worked for me when I come across this kind of problems is that just visualize the whole thing in a slightly enlarged way or a slightly exaggerated way. What will happen, say, when there is an external moment, these two flanges will try to open up, but the bolts are there in place to hold them together. So just visualize this whole process in mind. So in what direction the forces will get generated in the bolts. This is very important. So loads in the bolt will be acting along this direction. So if I see this view, the load is acting into the plane of the paper. Okay, that is something which you have to keep in mind as we go along. The first assumption is uh, even though these bolts are placed at certain discrete locations, I am replacing the bolts with a line load which acts in this fashion. Engineering is all about making correct assumptions, and I think it's a valid assumption. So I'm assuming some random distribution. You may not have to worry too much about the magnitude of this line load, but for the time being, let's assume that there is a line load which is acting along the circumference. And as you can see over here, it may not be constant as we move across the circumference. So let's assume it's a function of theta. So, and the units will be Newton per length. So I'm working with SI units. So the units of this particular quantity will be Newton per meter. Make sense? You have to make an assumption of the function as well. When it comes to picking the right function for this f of theta, let's have a look at this drawing once again. If I define my theta as shown over here, which bolt you think will take more load, this one or this one? So by intuition, it tells me this is the bolt which will take the maximum load. So I can always bring in my sine theta function here. What's so good about sine theta function? It assumes a value of 0 when theta equal to 0, and it assumes a value of 1 when theta equal to 90. So this bolt is located at a theta coordinate corresponding to 90 degree, while this particular bolt is located at a theta coordinate corresponding to 0 degrees. Given that, now I can assume my f of theta to vary like this. Where this is the maximum value of this line load and it varies circumferentially. So this is the bolt which corresponds to 0 degree. There the line load is 0, but as we move to this bolt, the theta is equal to 90 degree, and it is the line load, the load per unit length of the circumference is higher here. And always remember, this is true when you have a bending moment acting like this, trying to open up the flange in this direction. Let's sum up whatever we have discussed so far. So this was the joint we were talking about. So the effects of the bolt is replaced by a line load around the bolt circle whose intensity is in Newton per millimeter, and it varies linearly with distance from the neutral axis. Distance from neutral axis, this is your neutral axis. Distance from neutral axis is in fact r sine theta. So we assume some function like this for this line load. This is also varying linearly with distance from neutral axis. So this is a valid assumption. Now what we have to do, whatever be this line load, it has to be, or it should balance the external bending moment. Easier said than done. Now I should translate the same to a mathematical expression. For that sake, let's use the schematic. So here this is the line over which the bolts are mounted, and we assume that there is a load acting as shown over here. There is a load acting per unit circumference length. F of theta is that load. Units of this load will be Newton per millimeter. Now I can always write the load as this intensity times the length. So this point or this small material chunk is at a distance theta from the neutral axis. So this circumferential length will be r times d theta. So the load will be intensity times the length. So units also are in consensus. Now the load arm about the neutral axis is r sine theta. Now I am using this equation. Half of the moments or half of the moment should be balanced by the loads from these bolts, or from half of the bolts should balance half the bending moment. Makes sense? It's not that difficult to digest, I guess. So the moment due to the small bending moment due to this small load is this load times the moment arm. Again, see, the units are in consensus because when you multiply all these things together, you get Newton millimeter. And the integration is from 0 to pi because we are considering only half of the bolt circle. We can go ahead and solve this. At this step, can we take f outside the integral? No, we cannot, because f itself is a function of theta, and we assume that f will vary like this. I have already explained this. Rest of the things are plug and check. Once you do your mathematics correctly or the integration properly, you will arrive at this expression for the maximum intensity. The beauty of this expression is that now the maximum intensity is a function of the known parameters. The external bending moment is a parameter known to you, and similarly the radius of the bolt circle is also known to you. Now we have an expression for f of theta which goes like this. But still we have the very relevant question. What is the load acting on one bolt? Let me use this diagram to explain that. Say I need to find the load for this bolt. I can always make an assumption saying that whatever load is acting from 45 degree to 75 degree, that load goes to this bolt. Similarly, whatever load is acting from 15 degree to 45 degree, that load will be taken by this bolt. That's a valid assumption to make. Now let's translate the same into a mathematical expression. So for generality, let's say this angle is phi 1 and this angle is phi 2. Now all we have to do is evaluate the load corresponding to that bolt. So load on the bolt, as I just now explained, is equal to the effect of the line load over the arc associated with that bolt. Now I have to integrate this load intensity times the length over that arc region. So phi 1 corresponds to the beginning of the arc, phi 2 corresponding to the maximum theta coordinate corresponding to the arc. Once again plug and check. Once I do my maths, the force acting on one bolt turns out to be this much. Again, see, all quantities are known to me, and just check whether the expression is correct or wrong. You can always cross check the dimensions. So here the dimensions will be The whole expression is having the dimensions of Newton. It makes sense. So, using this expression, we can evaluate the load acting on one bolt. Isn't it beautiful? So, we had this whole flange joint which was acted upon by an external moment. Then we made assumptions one by one, and now finally we have an expression which tells us what is the amount of load acting on individual bolts. So, that's it for this lecture. Thanks for watching.